So in last class we have discussed initial conditions of an inductor, and we have discussed as current flowing through an inductor before switching equals to current through an inductor after switching. That means it doesn't support instantaneous change in current. So that we can say that current flowing through an inductor before switching equals to current flowing through an inductor after switching. So let us see the one more circuit here. Assume that so inductor connected to the voltage source, in between them, so the switch K is connected here. Alright, assume that when current IL equals to 0 before switching, what happens after switching in the circuit? That is what today's discussion here. I repeat, assume that IL equals to 0 before switching, then what happens the current in the circuit after switching. Alright, you can consider this point here. What is that? Before switching we said IL equals to 0. Can I represent that current as IL0 minus? That is equals to 0. Is that right? So before switching, when switch K is not operated, we assumed IL current equals to 0 in the circuit. Alright, then is that current equals to IL0 minus? Yeah, that current can be represented as IL0 minus. Okay, this is what current before switching, that we can call as T is equals to 0 minus. Okay, then can we say that it is equals to T equals to minus infinity? T equals to minus infinity. These two conditions are same here. Okay, assume that key is kept open for the long time interval. Switch K is kept off for the long time interval. Before switching, its condition was open. So that condition we can call it as T is equals to minus infinity. This is the case where switch is not operated. This is the case where the switch is not operated. Alright. Before switching, that consider the time interval just before switching, that is called as T is equals to 0 minus. I repeat. What is this condition? This condition is immediately just before switching. When you are about to operate the switch, the instant just before switching, that is called as T is equals to 0 minus n. Alright, and what we have assumed before switching, assume that there is no current in the inductor. So how to represent there is no current in an inductor? That is equals to 0 amperes. So if IL is equals to 0 before switching, then obviously the current just before switching, that should be equals to 0. Alright, now what is this condition? We derived it. Current flowing through an inductor immediately before and after will be same. Alright, so switch is operated here, so that after operating it becomes closed circuit. Then we have considered the time interval immediately after switching, so that is denoted here. T is equals to 0 plus, and in this case this current is denoted as 0 plus, that is equals to 0 amperes, because it doesn't change the instantaneous current flowing through it. Then how to represent this 0 amperes? It can be represented as open circuit. Have you understood this concept? So this is the circuit before switching. This is the circuit immediately before switching. This is a circuit immediately after switching. Have you understood this concept? Can you reply quickly? It is very, very important. Can you please reply? Okay, it will be repeated. Okay. Okay. Do not worry, I will repeat it. So let us erase everything. So what is inductor? What is property of inductor? It opposes the flow of the current. Is that right? So you don't get the rated current in an inductor when it is immediately turned on. It takes some amount of time. So it is the graph of an inductor. It is what current flowing through an inductor. Alright. So what happens? So the rated current will not be attained immediately when it is energized, when it is actuated. So you don't get the rated current through an inductor. It takes some amount of time to have the rated current in an inductor. So keep this point in your mind. Alright. Keeping that point in your mind, so we have derived current flowing through an inductor immediately before and after switching will be same. So current through an inductor immediately before and after switching, current through an inductor immediately before and after switching is the same. So instantaneous change in the current will not be possible in an inductor. These are some conclusions we discussed in the last class. Alright. So this is the switch. So the property of a switch is when switch is operated, it closes. Then before switching, it was open. So let us write here the status of the K. So when it is not operated before switching, switch was open. After switching, when it is operated, means when switch is pressed, it will be closed. It is what the status of the switch based on this diagram. Alright. And let us assume that IL is equals to 0 initially because the switch was open for a long period of time. The voltage source will not be connected to the inductor, so that no flow of the current in this case because of this condition. Before switching, when switch is not at all operated, it was open for the long period of time. So when it was open, the voltage source is not connected to an inductor. It is just like an open circuit. In that open circuit, assume that the inductor current is 0. Alright. So inductor current is 0. Is that the same current before switching? Inductor current is 0 when the switch is kept for a long interval of time. Is that the same current before switching? Yeah, obviously. So before switching, consider the time instant immediately before switching. Is that the same current flowing through an inductor when the switch is kept for a long time interval? And it is 0. And we can say that IL equals to IL 0 minus equals to 0 amperes. Alright. Consider the one more case. When switch is operated, then consider the time interval immediately after switching. consider an instant immediately after switching. What is that current? So that current is also called as I0 plus, and that is equals to IL0 minus. It is derived. What is that? Again it is 0. So that how to represent this 0 amperes? It can be represented as open circuit. It is what the circuit immediately before switching. It is what the circuit immediately after switching. So immediately before switching, the current is 0. Immediately after switching, even though the circuit is closed, we can say that IL0 plus equals to IL0 minus, that is equals to 0 amperes. See, this 0 amperes can be represented as open circuit. So these are the circuits immediately before and after switching. Keep that point in your mind. So if this is the time scale, if it is t is equals to 0, exactly immediately before, if we in this point only there is exist 0 minus and 0 plus. So they are measured in terms of milli, nano and even microseconds. You can just think. So these values will be there immediately before and after switching. They are one and the same. Almost they are same. T is equals to 0, T is equals to 0 minus, T is equals to 0 plus. Almost they are same. But they are not exactly same. So they do have micro, nano or microseconds of difference. At that time interval, we have derived before and after switching the current through an inductor is 0. So before switching I is equals to 0, then obviously after switching I is equals to 0. So 0 amperes can be represented as open circuit. Can you reply? Have you understood now? Alright. So first of all, the one thing should come in your mind, that is T is equals to 0 minus and T is equals to 0 plus. They are the instants immediately before and after switching, and they are measured in terms of milli, micro and nanoseconds. Keep that point in your mind. What you are discussing here, the concepts which are related to the time interval which falls in nano, milli and microseconds. Alright? One assumption should be there. Okay, good. So have you understood this? Alright. Now, let us consider one more case here. So, T is equals to plus infinity, which is called as the final condition. So, it is called as the final condition. What is that? So, the switch K is kept on for a long time interval. What happens? Inductor stores the energy, then there is a flow of the current. So for a long time interval, it attains, you can say, it attains its rated value. So once the inductor is completely energized, I repeat, once the inductor is completely energized, or it stores its possible all the energies, then it acts as a short circuit. Keep that point in your mind. Because you can see here, what is inductor value? L into dIL by dt. You can see here, L into d by dt of constant. Is that saying? Once switch is kept for a long time interval, you can see here the current value is becoming constant here. Is that right? You can see here it is a constant value. Once it is constant, what is differentiation of constant? That is 0. So that voltage drop across an inductor, what is voltage drop across an inductor? It is 0. How to represent 0 volt? It can be represented as a short circuit. What is conclusion here? The conclusion is, once inductor is energized completely, it acts as a short circuit because of this condition. Once it is energized completely, the current flowing through an inductor is constant. The differentiation of constant is 0. So voltage across an inductor is 0. So voltage is 0. That can be represented as short circuit. Have you understood this? There are 2 points. There are 2 points we have discussed. Before switching and after switching, current through an inductor is 0. So this is the final condition. This is the final condition when inductor is energized for a long time interval. So current flowing through and that is constant. Differentiation constant is 0. Then voltage flowing through, voltage across an inductor is 0. That can be represented as a short circuit. Understood? Can you reply? Okay. Let us see the one more condition. Let us see the one more condition. This is voltage. This is an inductor. Alright. This is, okay. It is switch K. It is switch K. Okay. We don't know. Before switching, assume that there is a flow of the current through an inductor. That is what we can say some A amperes. I don't know. So before switching, assume that there is the flow of the current in an inductor. It may be possible. So if there is a one more circuit connected to this, because of this voltage, there is no flow of the current because switch is open. Because of the other circuit, there may be a flow of the current through an inductor, and that is assumed as A amperes. That is assumed as an A ampere. Then when switch is closed, here before switching, what is current flowing through an inductor? That is represented as IL0 minus, and that is equals to A amperes. Then consider the case when switch is closed. That condition is called as a IL0 plus. Then we know that IL0 plus equals to IL0 minus, that is equals to A amperes. Then at that case, that inductor acts as a current source of value A amperes. I repeat. So this is the case before switching, current to an inductor is 0. So that it acts as an open circuit here. Alright. Because IL0 plus IL0 minus, that is equals to 0 amperes. So that 0 amperes can be represented as an open circuit. That is represented here. Same case, but IL is not 0 before switching. Because of some other networks, there may be a flow of current through an inductor. That is called as A amperes here. Before switching, obviously, current through an inductor is A amperes. Immediately after switching, this is the equivalent circuit diagram. And we know IL0 plus equals to IL0 minus. That is equals to A amperes. This A amperes can be represented as the current source of value A amperes. Means that before switching, if there is a current through an inductor, then after switching it acts as a current source. Keep that point in your mind. It acts as a current source. Have you understood? We have discussed 3 conditions here. Before switching, 0 current, what happens? Before switching, there is some current, what happens? And the final conditions. If the inductor is kept for a long time interval on, then it acts as a short circuit. Can you reply? Good. We go ahead. Then capacitor, we discussed. capacitor we discussed. So voltage across capacitor before switching and after switching remains same or else. So instantaneous change in voltage, instantaneous change in voltage will not be supported by the capacitor. Instantaneous change in voltage will not be supported by the capacitor. These were the conclusions we discussed in the last class. All right, and see here, it is a capacitor and we assumed current flowing through an capacitor is zero, so that there is no charge in the capacitor. There is no charge stored in the capacitor. So that what is voltage across capacitor? It is represented as VC0 minus, and what we have assumed, it is initially uncharged. How to represent capacitor as initially uncharged? Is it 0 volt? Is it 0 volt? Yeah. Then this is the case before switching. This is the case before switching. Then what happens? Immediately after switching, it is represented as V0 plus, that is equals to V0 minus, we discussed. It is equals to 0 volt. How to represent 0 volt? That is as short circuit. It is there. Right? Next thing here, I don't know, because of some other circuits before switching there is some charge stored in a capacitor. That is represented as V0 minus before switching. That is at V volt. That is represented as Q0 by C. I don't know, before switching there are some amount of charge stored in a capacitor. It may be charged because of the other circuits, or it may be charged and put it in a circuit. I assume that before switching the capacitor has some energy in it, that is equals to V0. Then what happens immediately after switching? V0 plus, that is equals to minus 0 minus, that is equals to V0, that is equals to Q0 by C. This is the equation for the capacitor. Means that once if the capacitor stored some amount of energy before switching, then it acts as a voltage source immediately after switching. In case of inductor, it acts as a current source. In case of capacitor, it acts as a voltage source. Is that okay? Then the last condition, the final condition. These two are the initial conditions and this is the final conditions. And we know the property of a capacitor. It is what the property of a capacitor. So charge stored in a capacitor will increase exponentially, and after some time interval, when the voltage source is connected to the capacitor for a long time interval, then the energy or the capacitor attains its rated voltage. Once the capacitor is completely charged, then it acts as a open circuit. Keep that point in your mind. I repeat, once the capacitor is completely charged, it acts as a open circuit. So that the voltage is connected to the capacitor for a long time interval. So because of this flow of the current, capacitor stores the energy. It starts charging. Once it is completely charged, then it acts as a open circuit. That is shown here. Then what is the difference compared to the inductor? Once the inductor is completely charged, it acts as a short circuit. Once the capacitor is completely charged, it acts as a open circuit. These are the differences. Then can you reply quickly? Have you understood this capacitor? In a capacitor, voltage before and after switching remains same, and capacitor acts as a voltage source, and once the capacitor is completely charged, it acts as an open circuit. 3 points you should remember in your mind. Instantaneous voltage change will not be supported by the capacitor. Before and after switching, voltage across the capacitor remains same. Capacitor acts as a voltage source. Once the capacitor is completely charged, then it acts as an open circuit. These are the 4 points you should keep in your mind for the capacitor. All right. Have you understood? Can we go ahead? All right. So let us summarize all these concepts, and we have not discussed regarding the resistor. Keep that point in your mind. Resistor supports instantaneous change. Instantaneous change. It supports means before switching and after switching, so values will be different across an resistor. Before switching, current may be changed. It can be represented in this fashion here. Current flowing through a resistor before switching, current flowing through a resistor after switching, they are different. Keep that point in your mind. Voltage across resistor before switching, voltage across resistor after switching, they are different because it supports instantaneous change. Keep that point in your mind. So that for that reason, in all these 3 cases, it is what before switching, it is what immediate after switching, it is what the final conditions. In all these cases, so resistor will be same. Resistor notation for the resistor will be changed, but values are different. Okay, let us consider an inductor. It is what before switching, assume that current flowing through an inductor is 0. Then immediately after switching, it can be represented as the closed circuit. And in the final condition, so it acts as a short circuit. Keep that point in your mind. Alright? And before switching, an inductor carrying a current through it, that is equals to I0. Immediately after switching, it acts as a current source. Then at the final conditions, it acts as a short circuit, and that current should be noted here. What is that? I0 current was flowing previously, so that is denoted here. These are the equivalent circuits: before switching, after switching, and final conditions. Let us come to the capacitor. Then charge stored in a capacitor is 0 volt before switching, means voltage across capacitor is 0 volt before switching because of there is no charge. Then it can be represented as a short circuit. Then at the final conditions, when the switch is kept for a long time interval, then it can be represented as an open circuit. Alright, then one more condition. Before switching, the capacitor is charged by a value Q0. Then immediately after switching, it acts as a voltage source of value Q0 by C. Then it can be represented in the final conditions as short circuit. Then initial value should be noted here, similar to this current source. It is short circuited, but the initial value is denoted with a current source. It is open circuited, but the initial value is represented with a voltage source. So these are it is an important table. If you want, you can take screenshot of it. So as an examination point of view, as a concept point of view, it is very, very, very important table. Revise it, be perfect in table, practice it like anything. So what happens before switching for the resistor? What happens after switching for the inductor? what happens before and after switching for the capacitor, then what are the status of the resistors, capacitors, inductors are the final conditions. So all things, so we discussed in previous two classes, all those discussions is explained with the help of this table. You should keep this table in your mind very perfectly and properly. It is essential. It is very, very important. Do you have any doubt in this table? Okay. So why resistor is represented same in all these cases? So this is the before switching case, after switching case, and it is final condition. And in all these three conditions, resistor is kept a same symbol. What is resistor is kept with the same symbol all in all these three cases. The first case is before switching, after switching, and when switch is kept for a long time interval. That is because the resistance doesn't it supports instantaneous change through it. Before and after switching, the values will be different. Okay, so we will see few problems on the concept in the next class by repeating the same concepts once again. Okay, so it's a time to wind up the class. We'll see in the next class. Thank you. Have a nice day.